Hi everyone, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, and I'm starting a new subsection. This is a pretty big chapter on group theory I'm doing, and I'm talking about a lot of different kinds of groups. Just finished talking about permutation groups, which is sort of abstract. These are more concrete, I'd say, rotational groups and symmetry groups of Platonic solids. These are 3D symmetry groups. I mean, the other geometric symmetry groups I talked about were symmetry groups of 2D figures, in particular, like regular polygons or rectangles. But now we're going to do 3D figures. These have more complex symmetry and also more complex groups associated with them. So anyway, let's begin. So what do we mean by rotational groups and symmetry groups of Platonic solids? First, I have to tell you what the Platonic solids are. Maybe I should skip ahead to that first. So here's a kind of wireframe diagrams of the five Platonic solids. There's five of them. They're shown on this picture. Tetrahedron is the simplest. That has just four triangular faces and four vertices and six edges. Um, it's its own dual. And then there's the octahedron, the second one shown. That's actually the dual of a cube. You get dual. I guess I'm sort of jumping the gun here. Maybe I should first tell you what these Platonic solids are. You've probably seen them before anyway, but I'm just going to go over them. So octahedron has eight triangular faces and six vertices and 12 edges. And a cube is its dual. And what I mean by dual is that if you take the center of any face and form a polyhedron resulting from connecting all those new vertices with edges, you get the dual polyhedron. So you can imagine you inscribe cube and an octahedron. You can go the other way too. You can take the vertices at the midpoints of each face of a cube, and that'll give you an octahedron. So cube has six faces, as I'm sure you guys all know. Like dice, a dice has six sides. Also has eight vertices and 12 edges. Icosahedron and dodecahedron, those are the two most complicated ones. Those are duals of each other as well. And the icosahedron has the most faces, has 20 faces, 20 equilateral triangular faces, and 12 vertices and 30 edges. And the dodecahedron, which is this dual, has 12 regular pentagonal faces as well as 20 vertices and 30 edges. So those are the five Platonic solids. And I was talking about, rotational groups and symmetry groups. What do I mean by that? Well, I kind of like what it says. The rotational group of each of these Platonic solids is the group you would get if you allow for arbitrary 3D rotations in these figures that make it look the same after you complete the rotation. So I think you can see. I mean, let me just switch to another picture here. These are kind of better. These are shaded 3D renderings of the Platonic solids. They probably look more like the real thing. I don't have models, unfortunately. If I did, I'd show them to you. But they're not that hard to make if you want to make models of five Platonic solids. Little origami models. Be my guest. I've done it before. I just don't have them with me now. You just cut out the. And I guess I should define what the Platonic solids are. They're kind of a three-dimensional analog of regular polygon. So yeah, I think you guys all know regular polygon is a polygon that has equal length sides and equal angles. And there's infinitely many of those. There's a unique regular polygon of dissimilarity with every number of sides, or if you like, vertices. Sometimes people call those n-gons. But what's a little weird in three dimensions, even though there's infinitely many in two dimensions, it turns out there's only five in three dimensions. So the equivalent definition in three dimensions would be a polyhedron. Polyhedron is now a three-dimensional analog of a polygon. And when we say it's regular, it means that each of its faces is a regular polygon. And it turns out there's only three possibilities for his faces. They can either be equilateral triangles, squares, or pentagons, regular pentagons. And not only are they all regular polygons, but the angles are all the same. It looks the same. Basically, it looks the same if you rotate it. I mean, it's equivalent from the point of view of any face or of any vertex. Basically, I don't know a better way to say that. But there's only five of them, and they're shown on this picture. And I think you can see, for instance, with a tetrahedron, that's probably the simplest one. Maybe it's better to move back to the wireframe pictures. Imagine you are rotating the tetrahedron 120 degrees about the center of any face. There's an axis that goes through the center of every face and the opposite vertex. I think you can kind of picture that in your mind. And if you rotate it 120 degrees, either way, clockwise or counterclockwise, you're going to get another figure that looks exactly the same as what you started. So that's a rotational symmetry of the tetrahedron. And it turns out, I'm kind of jumping the gun here, but it turns out that the group of the rotational group, the group of all rotations of the tetrahedron that leave it looking the same after you rotate them, and it is a group, because if you combine any two, you get a third one. I'm not going to prove it's a group here. I'll do that in a later lecture. But it turns out the group, and you also have to include the identity element, namely the rotation that doesn't do anything. That group has 12 elements, and it turns out to be isomorphic to A4, the alternating group on 4 symbols. Anyway. You'll have to take my word for that right now. Might as well tell you what the rotation groups of all these figures are. So yeah, for the tetrahedron it's A4. For the octahedron and the cube it's S4, the symmetric group on 4 symbols, which is just a group of all permutations of 4 symbols. For the icosahedron and dodecahedron it turns out to be A5, the alternating group on 5 symbols. And that has 60 elements. S4 has 24. And those are the rotation groups. But then there's the full symmetry group, which are twice as big. So there's other operations you can do besides just 3D rotations. You can also reflect. And remember, we did the same thing when we were discussing 2D figures. We did rotations, 2D rotations, or reflections. And, you get groups where you just have the rotations. Those are like the CN, the cyclic groups of order N. But you also get the groups DN, where you allow reflections as well, and those are twice as big. Has twice as many elements. The same thing with the symmetry groups of each of these Platonic objects. If you allow for a single rotation, it turns out, that'll generate along with all the, a single reflection, together with all the rotations I described, that will generate the symmetry group of each of these Platonic solids. So that'll give you a group that's twice as big, because half of the elements of the group will involve rotations reflections, and the other half don't. So, for instance, for the tetrahedron, you're going to get a group of order 24 now, if you allow for reflections. That group turns out to be isomorphic to S4 again, which is a little strange. But then if you do it for the octahedron and cube, you get groups of order 48. This is a group we haven't seen before. It's called the octahedral group. It's a pretty complicated group, but I'm not going to talk about it today. But that's the full symmetry group of the octahedron, or equivalently of the cube. And then for the icosahedron and dodecahedron, if you allow for reflections as well, you get a group of order 120. And that one turns out to be isomorphic to S5, the symmetric group on 5 symbols. So those are what the rotation groups and symmetry groups of the 5 Platonic solids are. I'm going to discuss each of these groups in detail in the next several lectures. And, it's a little complicated, but I think it's also fun, because you can play with these figures. Maybe I should make some of these figures so I can play with them and show you how they rotate. I might do that before I do the upcoming lessons. But anyway, that completes my video for today on rotation groups, 3D rotation groups, and symmetry groups. So thank you for watching. Long live math, and I'll see you guys next time. Bye.